Now, the spread spectrum is a communication method that spreads or distributes one or more discrete frequencies in time or frequency domains. There are two types of multiplex methods. One is circuit, which is a constant bandwidth, and also statistical, which is a variable bandwidth. There are two popular methods. The one is called direct sequence spread spectrum, DSSS. Examples such as GPS, CDMA, IEEE 802.11b and G. Frequency hopping spread spectrum, FHSS, such as TDMA, which is GSM, dynamic TDMA, Bluetooth, IEEE 802.11a, IEEE 802.16a, which is WiMAX. And also, as you can see, 802.11 uses both methods, depending on the A, B, or G. 3G is third generation communication for mobile telephones. So it's International Mobile Telecommunication 2000. IMT is the global standard for 3G wireless communication. IMT 2000 specified 6 radio interfaces, such as DS, direct sequence, also known as WCDMA, MC, which is multi-carrier, CDMA 2000, TD, time division, SE, single carrier, FD, frequency domain, and also OFDA, TD, wireless MAN, that also WiMAX. The reason why I'm actually putting all these here, you actually understand that 3G, although it's superseded by now LTE or long time evolution and 4G at the end of the day, it's a widely known communication method for GSM from a cellular point of view. Then Bluetooth is a radio frequency network communication protocol designed primarily for low power consumption. It also operates in the open 2.4 gigahertz band, such as wireless, and it uses frequency hopping spread spectrum. Bluetooth operating range are based on 3 power classes. Class 1, 100 milliwatt, 20 decibels per meter. The range is approximately 100 meters. Then class 2, 2.5 milliwatt, a little bit lower, 4 decibels, and about 10 meters. And class 3, which is a 1 milliwatt, 0 dBm at approximately 1 meter. Now, as you can see here, data rates varies quite a bit. We have version 1.2 Bluetooth at 1 megabit per second, and Bluetooth version 2 runs at 3 megabits per second. It is usually used for personal area networks, such as PAN devices, hands-free headsets for your cell phones, mouse, keyboards, and so on, game consoles. So it's more for a personal environment. Now, wireless multiplexing technologies, if you can look at that, there's a little table that I've created for you. You look at the technologies such as direct sequence spread spectrum. The principle, it spreads transmission over a wider frequency band, and the objective is to signal less susceptible to noise. Then frequency hopping spread spectrum. The principle here is that it's spread over rapidly changing frequencies, and the objective is not to interfere at one frequency, will only have a short-term effect. Also, orthogonal frequency division multiplexing, OFDM, where the signal is subdivided into sub-frequency bands, and the objective is to split high bandwidth transmissions into low bandwidth transmissions. Other multiplexing technologies include frequency division multiple access, FDMA. Principle there is to divide frequency into subbands, and the objective is to open several low bandwidth channels. Time division multiple access, TDMA, which splits the transmissions by time slices, and multiplexing between participants. Then code division multiple access, which multiplexes several signals into one signal, and multiplexing is performed on a digital level. The next thing we have to look at is some hardware issues. Let's look at patch panels. Now, patch panels provide physical cross-connect point for devices. It's an alternative to directly connecting devices, and it also allows for centralized management. Some of the patches can be manageable, and it just makes things easier to work with and connect and update. Modems is a modulator or demodulator. It converts digital signal into analog. Very little security, and there are risks like unauthorized modems such as PABX or PBX systems, fax machines, and then users sometimes on their desks. This technology, though, has been replaced, although it faxes extensively, but it has been replaced by the 3G cards and so on. Mobile telephony is undergoing a rapid development. It creates some security challenges. Most common in mobile phone technology is still GSM, which is Global System for Mobile Communication. It's got a network structure and very similar to a normal network. We've got base station subsystems. We've got network and switching subsystems. We've got our core network for GPRS, and then actually our operating support system. Now, at the data link layer, that's layer 2 of the framework, it is concerned with sending frames to the next link and defines the protocol that computers must follow in order to access the network for transmitting and receiving messages. It determines the network transmission format. Protocols that controls LAN transmissions are Media Access Control MAC and Logical Link Control LLC. Popular protocols that control WAN transmissions are X25, Frame Relay, ISDN, which is Integrated Services Digital Network, SDLC, which is Synchronous Data Link Control, HDLC, High Level Data Link Control, ATM, Asynchronous Transfer Mode, and HSSI, which is High Speed Serial Interface. Now, the media access control is at the data link layer addressing, or is a physical hardware address MAC, which is a unique address that is burnt into each NIC, network interface card, by the manufacturer. The hardware address is a 48-bit address expressed as 6 bytes. The first 3 bytes are vendor code and the second 3 bytes are serial numbers made up by the manufacturer. The MAC sublayer is responsible for media access. It controls how the workstations communicate over the network. And there are generally 3 types of media access, which is carrier sense multiple access, token passing, and polling. Now let's look at carrier sense multiple access, which means only one device may transmit at a time. You have carrier sense multiple access, CSMA. The carrier sense is when an internetworking device connected to a network, it first checks to make sure that the network interface has a carrier on which to send its data. Multiple access. All internetworking devices on the network are free to use the network whenever they like, as long as no one else is transmitting. And there's also 2 variations on this. We have carrier sense multiple access with collision avoidance, CSMA/CA, and then we've got carrier sense multiple access with collision detection, CSMA/CD. Now, when we look at the latter one, carrier sense multiple access with collision detection requires that all devices on the LAN listen before they transmit. This contention method is also known as Ethernet. If the 2 devices transmit at the same time, a collision will occur. After the collision, devices on the LAN will wait for a random amount of time before retransmitting data. Then, carrier sense multiple access with collision avoidance is a network contention protocol that listens to a network in order to avoid collisions. There is a contribution to network traffic due to, before any real data is transmitted, it has to broadcast a signal onto a network in order to listen for collision scenarios and to tell other devices not to broadcast. Now, an example of this is IEEE 802.11b radio frequency network. Polling is where a slave device needs permission from a master device. So a primary station checks a secondary station regularly at a predetermined times to see if it's got data to transmit. Secondary stations are not permitted to transmit until given permission from the primary. It's used mostly in mainframe protocols and an optional function of the 802.11 standard. It's fairly inexpensive. For those who are fortunate enough to have worked with token ring, this is token passing. A special frame circulates through the ring. A device must possess the token to transmit. Stations in the token passing networks cannot transmit unless they receive a special frame called a token. If the node does not have anything to transmit, it passes the token to the next station. Now, token passing is used in token ring, such as IEEE 802.5 and also FDDI. Deterministic, transmission delay predictable, and robust. The only problem with token passing is that it is single point of failure. If a station fails and the token can be passed further, the whole ring dies. Synchronous and asynchronous communication means that if it's synchronous, timing mechanism synchronizes data transmission. It's got robust error checking, practical for high speed and high data volume. Asynchronous, a clocking mechanism is not used, and the way it communicates, it will surround each byte with bits that mark the beginning and the end of transmission. Casting of packets, such as broadcast, the packet is copied and sent to all of the nodes on the network. A unicast is a packet is sent from a single source to a single destination. And then multicast, a source packet is copied and then sent to a group of destinations on the network. This is IP version 4. Now, when we look at switched network, we can either have a circuit switched or a packet switched network. A circuit switched network is dedicated circuit between endpoints. Circuit switching is a type of network switching in which a physical path is obtained for and dedicated to a single connection between two endpoints in the network for the duration of the connection. Endpoints have an exclusive use of circuits and its bandwidth, such as ISDN. A packet switch network where its data is divided into packets and transmitted on a shared network. Each packet can be independently routed on the network, such as X25 and frame relay. Virtual circuits, we have permanent and switch virtual circuits. A permanent virtual circuit can be established as an option to provide a dedicated circuit link between two facilities. A PVC configuration is usually pre-configured by the service providers. Unlike switch virtual circuits, permanent virtual circuits are usually very seldom broken or disconnected. In switch virtual circuits, these are generally set up on a per call basis and are disconnected when the call is terminated. A switched virtual circuit, SVC, is a virtual circuit that is dynamically established on demand and is torn down when the transmission is complete, for example, after a phone call or file download. SVCs are used in situations where data transmission is sporadic and or not always between the same data terminal equipment, DTE, endpoints. Now, there are WAN protocols such as X25, which is a protocol standard that defines how the WAN connection between user devices and network devices are established, maintained, and effectively operate. X25 devices include data terminal endpoints, DCEs, PSTNs like phones. X25 connection contains both switch and permanent virtual circuits within a physical circuit. Frame relay is an upgrade from X25 and a high-performance WAN protocol that operates at a physical and data link layer of the OSI reference model. Frame relay achieves high throughput with low delay by eliminating the overhead of error correction and detection. Asynchronous transfer mode is a dedicated connection switching technology that organizes digital data into 53-byte cell units and transmits them over a physical medium using digital signal technology. It requires high-speed medium like fiber optics. There's also carry offer 4 types of services such as constant bitrate, variable bitrate, unspecified bitrate, and available bitrate. We have WAN devices such as a modem. We've got a channel service unit or digital service unit, CSU, DSU, which is a digital interface device used to connect a router to a digital circuit like a T1. The CSU DSU also provides signal timing for these two devices. A multiplex or a MUX allows more than one signal to be sent out simultaneously over a physical circuit. A WAN switch is an internetworking device used to carry networks. This device typically operates at a data link layer. An access server is a concentration point for dial-in and dial-out connections. Then a gateway allows different types of networks to communicate. There's 3 main types of gateways, such as the address, protocol, and application. For example, a gateway between a radio frequency and IP or infrared and IP, and so on. Multi-service switch. This is a layer 2 or layer 3 device that provides interoperability between data link and network layers. For example, in a WAN, we have MPLS, which is multiple protocol label switching. And then in a LAN, we've got RSM, which is root switch module. A router or a router, devices that operate at the network layer of the OSI model. It's a LAN or WAN device that determines the best path to send network traffic based on costs and other network information. A router also has to share information with other routers, such as static or dynamic routing. Then IEEE 82.3 is the most popular LAN architecture. It supports bus, the star, point-to-point topologies. Currently supports speeds up to, here it says 1 gig, 1000 megabits to the desktop. However, 10 gigabit is in production. We have development. We have 802.3AE, which is 10 gigs, BG 40 gigs, BA 100 gigs, and BJ also 100 gigs. But this is only via 4-lane backplane and on copper in switches or routers. LAN devices, we have repeaters at layer 1, repeats electrical radio signal to extenders to extend the length of the network. We've got hubs and bridges at layer 2. Hubs of a central point of connection for cable segments in a physical star topology. Bridges are intermediate systems or switches that forward MAC frames to destination based on MAC addresses. Now, switches can be layer 2 or layer 3. It's essentially a multi-port bridge that functions at the data link layer. Each port of the switch make a decision to forward data packets to the attached network based on the MAC address that maps to an IP address. That is the ARP table. Each port on the switch is a separate collision domain, reducing traffic on the network. We have wireless local area network, which allows mobile users to remain connected and extends LANs beyond the physical boundaries or their perimeter. Example here is a Pringle can, which is used in test environment to see how far a antenna can be made directional. Supposedly the aluminium inside the Pringle can allows the signal to be directed. We have wireless protocols such as WAP, which is Wireless Application Protocol for internet working between IP and cellular services. WAP is a protocol suite from data link to application layers. We have cellular, which is time division multiple access, which supports data transmission. Also, code division multiple access, CDMA, which supports data transmissions. We've got the global system for mobile communication, which supports data service using GPRS or general packet radio services. And then finally, we have 802.11, A, B, G, or N, and also some later technologies running we'll see later. This is a beacon frame announced which presents to provide service set identification, SSID. Access point placements is important. We must not count on hiding the access point from an SSID point of view, as it can be scanned by certain software. And from a corporate environment, we need to worry about possible rogue access points, where somebody can put an access point down a little bit stronger than yours, and users are duped into getting there and releasing or entering their user IDs and passwords for a hacker to obtain that. Some authentication can be done at the wireless access point, which is paramount to the security of those wireless LANs. We can have open system authentication. We can have a shared key between devices. We can do MAC address filtering to only allow certain MAC addresses to come into our network. And then EAP, which is Extensible Authentication Protocol. Now, when we look at this, we can have wireless encryption such as WEP. Now, why the equivalent privacy? WEP is an open system and shared keyed authentication. It is weak and crackable using software like WebCrack. And it's based on the initialization vector and RON's code version 4, RC4. Assumed RON's code because it was developed by Ron Rivers. And there's a predictability and should not be used. We've got Wi-Fi protected access, WPA, which have got temporal key integrity protocols such as TKIP, and then Wi-Fi protected access version 2. It replaced the WPA. It's got counter cipher block mode with block chaining, message authentication code protocol, or CCMP, in CCM mode. And if you look at that domain 5 and come back to domain 2, you'll understand how that effectively ensures better encryption. Wireless encryption, here's a little table you can go through. For example, 802.11 dynamic web, we've got WPA and WPA2. Go through the access control to see what it uses. As you can see, it uses 802.1x, pre-shared key, authentication EAP or pre-shared keys. And what's important here, and from an encryption point of view, WEP does RC4, TKIP with RC4, and then as you can see, WPA2 has much, much better AES, which is Randall, with counter mode. Integrity is none on WEP. And as you can see, Wi-Fi Protectors has got some integrity controls, the message integrity control, and then also WPA has got AES, which is Randall, which is cipher block chaining, and then media access code. Just for some wireless standards, we've got 802.11a, 54 megabit, B, 11 megabits, G, 54 megabits, and also N, which is MIMO, which stands for multiple input, multiple output antennas. and that runs between 54 and 150 megabits. Now, all of these can run at a double the speed if it's duplex. We've got new developments such as 802.11 AC, which is running at 1 gigabits per second, and then also 11AD in development at 7 gigs, which is called Y-gig, and then Bluetooth is also a wireless standard. When systems want to communicate on the network, it needs to know how to communicate, IP addresses to MAC addresses, and this is where we have the address resolution protocol, which is a request and reply protocol that runs encapsulated by the line protocol. It is communicated within the boundaries of a single network, never routed across inter-network nodes. In IP version 6 networks, the functionality of ARP is provided by the Neighbor Discovery Protocol, or NDP. Now, reversed address resolution protocol has been rendered obsolete by the bootstrap protocol in the Unix environment, and possibly at the dynamic host configuration protocol, or DHCP, in the modern systems, which both support a much greater feature set than reverse address resolution protocol. Now, other issues is when we look at authentication and network communication at this level is password authentication protocol, PAP, identification and authentication of remote entity point-to-point protocol, PPP. It uses a clear text, reusable static password, high risk of course, supported by most network devices. Now, PAP is the protocol that two entities share a password in advance and use password as a basis of authentication. When we look at CHAP, or Challenge Handshake Authentication Protocol, CHAP is an authentication scheme used by point-to-point protocol, PPP servers, to validate the identity of remote clients. So these following steps happens. Step 1, after the completion of the link establishment phase, the authenticator sends a challenge message to the peer. In step 2, the peer responds with a value calculated using a one-way hash function on the challenge and the secret combined. And in step 3, the authenticator checks the response against its own calculation of the expected hash value. If the values match, the authenticator acknowledges the authentication. Otherwise, it should terminate the connection. Then at random intervals, the authenticator sends a new challenge to the peer and repeats step 1 to 3 above. In the next layer, when we look at the network layer, that's layer 3, it is the network layer. It is responsible for addressing and delivery of packets. It knows the address of all neighboring nodes in the network. Packages output with the correct network address information. It selects the routes. It recognizes and forwards to the transport layer incoming messages for localhost machine domains. Example, IP protocol and netware IPX. At the TCP IP layer, the Department of Defense created TCP IP to provide robust communication during wartime. The TCP IP protocol suite is the standard for computer communications in today's network world. And then also at the internet layer is the OSI network layer, layer 3, that contains addressing information, control information, and enables packets to be routed, such as ICMP, which provides control and messaging capabilities. That's Internet Control Message Protocol. ARP, which determines the MAC address for a known IP address, and reverse ARP determines the IP address from a known MAC address. Now, this is an example of an IP structure, which you can actually look at. It's got quite a few little attributes. My recommendation is to download, if you don't have already, Wireshark, install it on your machine and sniff your network a bit and look at the packets and look at the content of the packets and what happens on the network. This is your best bet to understand how communication works inside a network. Then if we look at IP version 4, it is an internet protocol address. It's 32 bits only, where IP addresses are logical addresses and not physical. It includes a network ID and a host. Every host must have a unique IP address, and IP addresses are assigned by a central authority. Now, we have different classes here, class A, B, and C in our network. As you can see there, from 0 to 127.255.255.255, class B 128.0.0.0 to 191.255.255.255, class C is 192.0.0.0 to 223.255.255.255. Then class T is my multicast address from 224.0.0.0 to 239.255.255.255. And then finally class E, which is experimental, 240.0.0.0 and up to 254.255.255.255. IP version 4 is a method for connecting multiple computers, and this is network address translation to the internet or any other IP network using only one IP address. There is an RFC 302 if you want to look in detail into it. The increased use of NAT comes from several factors due to the fact that we have a shortage of IP addresses in the world, special security needs, and also ease and flexibility of network administration. Now, RFC 1918 reserves the following private IP addresses for NAT. And these include things like Class A, my 10 range, Class B, my 172.16 to 172.31 range, and Class C, 192.168 range, and a from 00 to 255.255. Now, a private address is also known in the networking terminology as a non-routable address, meaning that if it goes outside your network, it will go maybe 1 or 2 hops, and then routers will not route it further because it hasn't been configured for that. Due to the fact that we have limited addresses worldwide, it has been extended to IP version 6. This is the next generation protocol designed by the IETF to replace the current version of version 4. It's got a larger IP address space. IP version 6 is 128 bits instead of 32 bits. It's designed primarily to address the shortages of IP version 6. Also, there are issues like auto-configuration, which uses a stateless host auto-configuration. That mechanism is mandatory and is much simpler than IP versions 4 DHCP. Also, security is being enhanced where IPsec support is mandatory. Quality of service flow label, IP version 6 was designed to support for traffic engineering like diff-serve and also int-serve, such as RSVP. Multicast is mandatory in IP version 6 and IP version 4 uses ICMP. When you look at IP version 6, there are a couple of attributes. There's a priority attribute within the packet, which enables the source to identify the desired delivery priority of the datagram. We have a flow label used by a source to label those products for which it requests special handlings in the IP version 6 router. We also have a payload length, which is the length of the payload in octets. We have next header, which identifies the type of header immediately following the IP version 6 header. Hop limit, which is an 8-bit integer decremented by 1 by each node that forwards the datagram. A source and destination address, which is 128-bit IP addresses. When we look at the implementation, there's a couple of ways of actually looking at it. And there's also an RFC for this, 438 if you want to look at it in detail. We have IP version for compatible IP version 6 addresses and also IP version for mapped IP version 6 addresses. What it says that IPsec is mandatory in IP version 6, but biggest implementation challenges were updating the key exchange protocols and ciphers, IKey version 2, also known as IKE version 2, and then also establishing a security association on an internet scale. RFC 5996, which is the Internet Key Exchange Protocol version 2, IKE version 2, 2 phases, IKE SA and Child SA to better facilitate IPsec deployment. Okay, IKE version 2 is not backwards compatible IKE version 1. And then RFC 4301 is the security architecture for IP, which added a peer authorization database PAD to provide a link between SA management protocol and the security policy database. Then, as previously we've seen in IP version 4, we had broadcasts, unicasts, and multicast. This now for version 6 has been updated to unicast, where a packet is sent from a single source to a single destination, very similar to IP version 6. We've got a multicast address. A multicast address identifies a group of IP version 6 interfaces. The source packet is copied and then sent to a group of destinations on the network. Anycast. An anycast address is assigned to multiple interfaces. The source packet is delivered to the nearest interface. Now at network layer 3, the Internet Control Message Protocol is used to exchange control messages between gateways and hosts regarding the low-level operation of the Internet. And these are implementations such as ping and traceroute. Now, ICMP is encapsulated with the IP packet. Certain types are encapsulated inside the ICMP request. For example, type 8 is an echo request, which is actually the ping. Also, if I change it programmatically to other things like type 13, timestamp, 15 information request, and 17 address mask request. And as you can see, there's a lot of information from a network you can obtain using the ICMP. Now, a local area network, we've seen that before. It's in a relative small area. Most LANs have connectivity to other networks. Virtual LANs are software-based LAN segments implemented by switching technology, which allows ports on a switch to be grouped into single broadcast domains. This allows devices to be logically configured as if they were on the same network without regard to their physical location. When we look at virtual local area networks, or VLANs, membership can be classified by port, MAC address, and prototype type. For example, a membership by port, where the main disadvantage of this method is that it does not allow for user mobility. If a user moves to a different location away from the assigned VLAN, the network manager must reconfigure the VLAN. Membership by MAC address. The main problem with this method is that the VLAN membership must be assigned initially. In networks with thousands of users, it's not an easy task. Administration is high. Membership by protocol type. The network IP subnet addresses can be used to classify VLAN membership users that can move their workstations without reconfiguring their network addresses. The only problem is that it generally takes longer to forward packets using layer 3 information than using MAC addresses. VLAN membership can also be based on application or service or any combination of the above. Now, wide area network is a network connecting local area networks or access points. Connections are often shared and tunneled through other connections. Public switch telephone network, PSTN, is a circuit switch network, and PSTN may be subject to attacks. Integrated service digital networks, or ISDN, they're used two types of channels and comes into two varieties. We've got a bearer channel, B, and a D channel, delta channel. And as you can see, they're running at different speeds, where B channel is 64 kilobits and D channel is 16 kilobits. Basic rate interface can give me 2 B and 1 D channel, which gives me 144 kilobits. A primary rate interface in North America is 23B bearer channels and 1 delta channel, which gives me 1.55 megabits. That's my T1 line. And a PRI in Europe and Australia gives me 30B channels, and 1D channel gives me 2 megabits, which is an E1 channel.